Our speaker today, Ron Vescadeghian, comes to us originally from Berkeley, and I think by way of MIT or something, and he's he's from Berkeley, and he just got tired of all that sunshine, so he moved to Michigan. So I'll let him tell you about what he's interested in, and I think you're wrong.
Totally. Thanks for the intro. Thank you all for coming. This is great. I guess everyone's really excited about the end of the semester. So you celebrated by coming to the control seminar. Fantastic. Okay, so I'm going to talk a little bit about lifting to infinite dimensions and what this title means. It's actually kind of hard to give a talk at your home institution, by the way, because you also want to sort of give a little bit of a shout out to everyone that does cool work with you and whatnot. So I mean, I should warn you that nothing will work. Okay, here we go. Okay, maybe I'll just stick with this. These are the folks who are actually doing, some of the folks who are doing the heavy lifting. They do really, really great stuff. I will talk to you a little bit about what they do. Broadly speaking, the work that I do in my group is divided into sort of two different pieces. The first one is this area of prehabilitation and rehabilitation. And in this area, we sort of divide our problems into three different domains. And the idea here is that we want to be able to look at people as they're moving around in the world non-invasively and try to be able to develop techniques that can diagnose different types of biomechanical deficiencies. So one of the things we've actually done is work with some collaborators up at MedSport. So Ashish Bedi and Darlene Yao, and these are my students up here. And what we've done is actually develop this really, really cool data set. And what this data set does is actually look at a bunch of people who've been rehabbing their ACL after they've gone through a reconstruction surgery. And what we've done is build this gigantic data set where we're essentially collecting their behavior while they go through a variety of different exercises. And what we've shown, in fact, is that we can actually recover a lot of the dynamic properties of their behavior without actually attaching sensors to them. And what we're now doing is working with Ashish and Darlene to look at sort of longitudinally what types of motions and what types of properties, be they dynamic or kinematic, correspond to re-injury or correspond to a higher risk of ACL injury in general. The other thing we look a lot at is trying to understand what it means to be stable. And so what we've done is actually work with some collaborators again. Art used to be here, Kuo, and his student Xiaoyu. We've done a lot of work on basically building data sets where we perturb people while they're doing real motion. So I actually think this is my student Patrick. And Patrick is actually up there, and he's walking around. And what we've done is attach cables to Patrick, and we're perturbing him. And we're seeing how much of a perturbation he can try and tolerate. And what we do is try to understand how stable a person is by using control theoretic concepts like a region of attraction. And so, in fact, what we've developed are these techniques that can generate a region of attraction for different types of locomotion. And in fact, what we've done recently is shown that these different types of regions of attraction actually coincide with just how stable someone is. So if we actually perturb them, we can predict what level of perturbation, what type of perturbation actually corresponds to them having to use a different type of control strategy. And it's been shown in the literature that having to switch arbitrarily between different control strategies typically corresponds to a higher likelihood of falling. So the last thing, and this is an area that I hope to get more into, is translating all of these sort of ideas of region of attraction and whatnot into actually doing control design for prosthesis and orthotics. But this is an area that we have not done too much exploration around, but it's an area that we're looking to get into more and more. The other area that we do lots and lots of work in is in the automated and connected vehicles domain. Again, there's sort of three different styles of problems we like to look at. One is, can we model people at scale? And my collaborators here, Xiao Du in particular and Juan Kim, have done really, really incredible work in building these beautiful data sets of people actually in and around Carytown, where we've collected data from cameras and LiDAR and all sorts of stuff, and actually been able to reconstruct their morphology at really, really large distances, and actually use that information to do really, really cool things when it comes to prediction and whatnot. The other things we've done is actually look at sort of estimation problems. And typically people think of estimation in automated vehicles and they think of things like SLAM. That's great. One of the things we've actually done is use windshield wipers, for instance, to actually estimate rainfall rates. And this is with collaborators Matt Bartos and Branko Kirkez in Hyungju Park. And what we've done is actually shown in Ann Arbor using instrumented vehicles that we can actually improve the accuracy of rainfall prediction and actually improve it so much so that basically, we can try now and basically try to control water networks and whatnot. And my colleague here, Branko Kirkez, can talk about that at great length. It's a really, really cool way to leverage automated vehicles in a way that people don't nominally think about. So it's really, really cool work. And the last thing we think a lot about in my group is actually, driving. And Michigan presents, a really, really interesting challenge when it comes to driving. So you'll notice none of these people up here are actually from Michigan. This is my first time in Michigan. As James said, I came here from Berkeley, and I grew up in Southern California. My first time in Michigan was in Sault Ste. Marie in February in 2011. And what we were doing back then was trying to drive this Jag at really high speeds on ice and try to use MPC to try to do lane change maneuvers and whatnot. It's really hard. And frankly, it was super, super cold. They had me standing outside recording this, and I can still remember that. In any case, all of these sort of areas have their own challenges. So for example, when it comes to modeling, it's really hard to model interactions and do it in a way that's non-invasive. When it comes to estimation, it's really trying to understand the state of the world. The world is changing dramatically all of the time. Your models are nonlinear. It can be really hard to figure out what's going on. Again, when it comes to control, our systems are nonlinear or hybrid. It's really hard to control these types of systems. But in particular, my group is really excited about this strategy where we translate all of these different types of problems into infinite dimensions. And what do I mean by that? Well, what that means is we can represent our dynamics as linear in an infinite dimensional state space representation for a system. And when it comes to nonlinear programming, so for example, if I'm trying to do control design using model predictive control with a nonlinear system, well, that can be really hard to solve in practice because I have to solve a nonlinear program. But what we've been able to do is, by lifting, translate these problems into convex programs that have nice properties in terms of approximation and whatnot. So I'll talk about that today. And the areas that I'm really going to speak about are these ideas of trying to do not at fault autonomous vehicle control. And I'm not a jerk like my advisors are. I let my students go to Sydney and control a self-driving car down there. And in fact, what they're doing now is driving this vehicle in and around the Sydney campus. And you'll notice there are people around and whatnot. And it's actually doing all of the control in a provably not at fault way. And I'll talk about what that means, without requiring any human intervention, whatnot, all on the platform itself. And it's doing all the sensing, everything online. And hopefully, I will also get to talk about some work that we've been doing in data-driven control on soft robots. And in this instance, what we're doing is collecting lots of data, building models in infinite dimensions that translate into a linear representation that allows us to do things like model predictive control, even though the models for these soft robots and the construction of them can make them really, really nonlinear. So hopefully I'll get here. Chances are not looking great, considering I have about 90 slides, but we'll see. OK. So that's going to be sort of an outline for my talk. I'm going to start off by talking about that reachability-based trajectory design in order to design provably safe real-time control for autonomous vehicles. We'll start off with the static case, where everything in the world is going to be not moving. And then we'll jump into the dynamic case. And then hopefully we'll get into the soft robot stuff. By the way, if you have questions, interrupt away. OK? So the way I always like to start thinking about these problems is a cartoon. So as my students know, I'm a terrible engineer. And so everything for me starts off with scratches on a whiteboard, or in this case, on a PowerPoint slide. So pretend that this is our car in blue, and we have another car in red. And our goal now is to take this blue car and get to this green line. And in practice, in automated vehicles, what we typically have is something like a route planner that generates these types of plans, like turn-by-turn information for us. And so this type of representation of the problem would correspond to, for instance, you being presented with a set of instructions that you have to undertake in order to satisfy some objective, like here's a Google Maps representation for getting from here to the airport. Right? And it provides you these turn-by-turn instructions. And what we want to be able to do is leverage those same turn-by-turn instructions in order to travel around this red car. The key idea here is that model complexity is really, really important. So our colleagues in the Auto Lab, for instance, can build these really, really nice models of vehicles that are really high dimensional, can be really nonlinear, and hard to grapple with in real time in a way that allows us to say anything about safety. On the other hand, there are really, really simplistic models of a vehicle where I model the car, for instance, as a double integrator. That model is really, really simple. But the trade-off here is it doesn't really represent the true dynamics of the vehicle. And our goal is somehow to understand where we want to live along the spectrum. And making a choice unnecessarily forces us to decide that we're losing something in terms of model fidelity. So our goal may be to generate a path. And maybe that path in continuous time looks like this in green. And we notice that this green path, maybe with this high fidelity model, is actually intersecting with this obstacle. Well, unfortunately, in practice, the way that we think about representing that trajectory is typically by using a really simple model and discretizing time. And when we discretize time, we generate something that looks like this dotted green line. And the problem here is that dotted green line may look to us like it's safe, but in fact, we know that it's realistic, that is, its representation when we actually run the car is going to look like that solid green line. And what that means is we may say that we are safe in this instance, but in fact, we are not actually safe. So again, the challenges here are sort of straightforward. Quick computation may not be safe on the left-hand side. Slow computation, difficult to guarantee computation is feasible on the right-hand side. And what we want to try to do is live somewhere in the middle where we can say something about safety and balance model complexity while capturing modeling error. So why is that so important? Let's come back to this video. And typically, many people do control design by using things like model predictive control, where they linearize about a trajectory that they've pre-planned. It's really great. You can hear the wind. This is when it's less great. And I apologize for the cursing in advance. This is me sitting in the back of the car. By the way, the person sitting in the front of the car here is actually one of the designers of the Tesla Autopilot. It's a fun, fun story. And you'll see our safety driver is holding on for dear life. He trusts us. And that's us crashing the car. So in practice, you can do really incredible things with things like model predictive control. But in practice, being able to verify that it's going to operate safely is a really hard challenge for us. And what we want to be able to do is develop techniques that we can verify are actually going to behave correctly when we generate them. And what I'll say is there's a really rich problem. Lots of people, including those at Michigan, many, many people at Michigan have been thinking about this problem. So my students have this really nice sort of breakdown of the different approaches to think about this problem. The first set of methods they call check methods. And the way that these check methods work is that you pre-design a trajectory or a family of trajectories, and you check at runtime if that pre-computed trajectory is actually safe. And the way that these techniques work typically is things like using zonotope methods, where you propagate uncertainty about that nominal trajectory that you've designed. This is really great, and in fact, you can do really cool things in terms of verifying that a trajectory is safe at runtime. The challenge is if your trajectories are not rich enough, you really can't say very much about safety. So for instance, as you're driving along, if your library is not rich enough, and all 5 of, let's say, your trajectories are unsafe, well, then you'd have no idea what to do. And in practice, that can be really problematic. On the other hand, there are these other approaches that we'll call correct approaches. And what they try to do is modify a generated control input at runtime in order to ensure that it can behave safely. In fact, there's a variety of different techniques that try to do this. So I'll refer to this, this really nice lit review by Ilya. You guys should check it out. It's called Reference Governors. I mean, reference governors have been developed here. I mean, Gilbert, for example, has done really, really amazing work, and his students as well have done great work in this area. The idea is that, again, as I'm running my system forward, suppose I apply a reference control input or a reference trajectory that I want to try and track. Well, what these methods do is figure out a way to correct that trajectory at runtime in order to ensure safe behavior. The challenge here is that generalizing these approaches to nonlinear systems can be hard. And in practice, again, trying to do this for arbitrary situations can be a bit difficult. Although I'll say that this approach is really, really rich. So there are really great things you can do with it, as I'll show you later on, actually, in my talk. Jesse, Nechmier, and many, many others, Wei Peng and his students, and their students have taken these ideas associated with control barrier functions and done really amazing work when it comes to things like adaptive cruise control and lane keeping. And the idea here is that, again, you modify a trajectory at runtime or modify an input at runtime in order to ensure safety. These approaches, again, are really great. They tend to work sort of in specific situations, although there have been nice ways to try to generalize this. So Yuxiao Chen, who graduated, I think, a year ago, has been doing some really cool work where he has tried to generalize this type of approach to arbitrary path planning. The translation typically turns into an integer linear program, and that can be really hard to execute at runtime, where the environment may be changing, et cetera. Next are these approaches that use the Hamilton-Jacobi-Bellman equation. They're called fast track. Sylvia, I actually think, is giving a talk here next week, if I remember correctly. You guys should check it out. It's really great. Again, they develop things that look a lot like barrier functions that modify a trajectory or know how to modify a trajectory at runtime. The way that these are solved is by using a level set method. The level set method is not provably outer approximative, so the guarantees that they're able to make on pencil and paper are pretty limited at the moment, but they're working on it. The last set of approaches are what I'll call select. And what these try to do is instead of correcting a trajectory, they select a trajectory that they know at runtime is going to be safe. And the ways that these can work, for instance, can be by having a finite set of trajectories and then checking one of them at a time, or an approach that my students have developed, which we call reachability-based trajectory design. And it's a really cool idea, and that's what I'm going to talk about next. And the idea, again, is that you have a family of trajectories, and you're actually able to say something about provably being safe and always being persistently feasible in a way that's actually useful so that you can say something about safety. OK? How does it work? So let's start off with an example. And again, this is just an example. As we'll see, this approach will generalize quite well. So if I look at vehicle dynamics, they look really, really nasty. So this is a really simple model of a vehicle that Gabor Rose, for example, could probably talk about and teach about at great length. What I'll mention just quickly is that these tire forces that are written down here are tremendously nonlinear and are really, really nasty. And in practice, it's really hard to describe, or apply methods to speak about safety for this class of systems. What we want to be able to do is design control inputs that actually ensure that this can operate safely at runtime. And the important thing to keep in mind is that our obstacles or things that we want to avoid are typically only represented by our first three states here. So our first three states are our position in the world. And in this instance, if we were in a 2D world, it would just be our x and y position and our heading. And what my students realized is that this is a really complex model, but really safety in this instance can be boiled down to just thinking about those first three states. And what they thought is, hey, why don't we just drop the rest of the dynamics and instead think of our system as just a simple kinematic model? Well, in that instance, you're giving up a heck of a lot, right? Obviously, a kinematic model and a dynamic model are not the same at all. But they can be related to one another. And the way that we'll relate them to one another is by introducing a term in a second. But before I do that, I should mention that this velocity and omega, we're going to treat those as trajectory parameters. And just to save myself some space, you can think of them as some gains being selected from some trajectory parameter space. OK, so the way that we're going to try to model the difference between this kinematic model and that more complex model is by introducing a term that I'm going to call disturbance term. And this disturbance term is essentially going to describe the gap between that dynamic model and that kinematic model. And in order to describe that gap, it needs to satisfy this assumption. And what this assumption is saying is that over a certain time horizon, from 0 to capital T, we can bound the difference between the high fidelity model and this simple kinematic model according to this inequality. And if we can construct this G to satisfy this inequality, in fact, this dynamical system with disturbances drawn between -1 and 1 as a function of time can actually describe the gap between this low-dimensional system and the high-dimensional system. And what I mean by that is that this low-dimensional system has a selection of a disturbance input that is capable of describing the behavior of that high-fidelity model. And so in practice, this much simpler model is capable of accounting for the difference between that high-fidelity system and the low-fidelity system, and we'll see how we can leverage that in a moment. OK, so let's come back to this picture. This is our state space X. This is our initial vehicle set. So this is our initial position of the vehicle. Suppose it's continually moving along. And what we have are a set of trajectory parameters, and they're drawn from this space capital K. Well, in practice, if I search over all possible Ks, what I'm left with is this sort of bell-shaped curve of all of the possible trajectories for that simple kinematic system. OK, so in practice, we have our simple kinematic system. But now we add in a disturbance. And what this disturbance is doing is describing sort of a volume of possible trajectories for that low-dimensional system as I carve out all possible disturbances d of t. And in practice, what that volume is describing is all possible outcomes described by that low-dimensional system that in one of those outcomes contains the behavior of the high-fidelity system. OK, so if we go back to this drawing, what that means for us is if I pick something over here, OK, and maybe this is some obstacle. In fact, that obstacle is going to map to a set of trajectory parameters on the left-hand side. And in fact, being able to speak about safety can be described as just figuring out which set of trajectory parameters actually are unsafe because of this projection backwards from this set in the state space to the trajectory parameter space. So what we want to be able to do at runtime is be able to select trajectories that stay out of those unsafe trajectory parameters and be able to manage that set in a way that allows us to do online planning. Okay, so that's what we're going to describe. If we do this, by the way, because of the way this disturbance input is selected and because of the way that assumption is formulated, this ensures that the high fidelity model will not actually crash at all. Okay, so what are we going to do? I'm going to step through 3 tasks. The first task is going to be computing the forward reachable set of the system, and we're going to do that offline. Once we have that offline representation, it'll allow us to be able to describe the set of safe and unsafe trajectory parameters in an online fashion, as I'll describe in a second. And the last bit is in order to ensure persistent feasibility, that the car will never run into anything, we need to ensure that we can actually select the time horizon correctly, and I'll describe that process at the end. Everyone with me so far? Any questions? It's very hot in here. Okay. Okay. So the first bit is we're going to describe how to compute the forward reachable set, and this is where the infinite dimensional perspective will appear. In particular, what we're going to do in order to compute the forward reachable set of the system is that we're going to perform an optimization over functions. And it'll turn out that this optimization over functions will be a linear program over functions. But since we're optimizing over the space of functions, it'll actually be an infinite dimensional linear program. So the first part of this optimization problem is we have this V, W, and Q. V, W, and Q are going to correspond to the functions that we're optimizing over. And what we're going to do in our cost functions is try to minimize the volume of W. And that d lambda is going to correspond to the Lebesgue integral in this instance. What we're going to show is that Wx of k converges to the indicator function on the forward reachable set. And I'll show you how that works in a second. In order to do that, we're going to have a litany of constraints. Okay, and this is where we can flip over to this writing here on the right-hand side. Okay, so what are these constraints doing? In fact, what these constraints are doing is writing down a Lyapunov function for us. And in order to understand that, let's start off by looking at v. So v is a function that by the fundamental theorem of calculus, I can write down its flow along trajectories of the system by using this equality. The next line here is just me taking this total derivative and describing it in terms of these partial derivatives. The next line here is actually the first time I'm using one of the constraints that's written down here. In fact, what these pair of constraints, this one and this one, are doing is actually bounding the effect of the disturbance, d, by using q. And so q, in this instance, is describing sort of all possible things that that disturbance input can do. And in fact, that's why this inequality is appearing. So I went from equality and inequality. And then the last line here is actually just using the first equality up here and this bottom equality down here, or inequality down here. So in fact, what this is telling me is that along flows of my system, I have this inequality being satisfied. And in particular, this is an arbitrary initial condition, and this is an arbitrary time along that trajectory. So what I'm getting is the forward reachable set described as a level set of a system by selecting a particular value of k. So for each selection of k, I'm describing what the flow of the system is by using this level set object. And in particular, again, v is acting like a Lyapunov function. It decreases along trajectories of the system. And in fact, that last constraint allows me to describe the entire forward reachable set just by using w. And that's what that inequality down there is doing. And as a result, what we can show is, in fact, a solution. And by the way, it's a linear program. I can show you why in a second. The solution to this linear program is going to generate a w that for any selection of k, this value of x being greater than or equal to 1 is going to correspond to an element that can be reached by our system by that selection of k. In other words, the one super level set of w contains the forward reachable set of the high fidelity system because of the way the disturbance is defined. By the way, why is this a linear program? Each of these constraints in here is a linear constraint. It's pointwise. And that's kind of the difficulty with this problem. I actually need to enforce all of these constraints over an entire set. And in fact, that set is what's going to create a nightmare for us. Okay? The good news, and I won't cover it here, but it's tremendously interesting, is that for certain classes of dynamics, polynomial, rational, trigonometric. In fact, you can generalize this a little bit more than that. There exists a sequence of semi-definite programs with vanishing conservatism that actually solve this linear program. And what we can prove is that, in fact, the solution to any STP, any of these STPs, is a polynomial function W whose one super level set for each k coincides with the FRS under k. So what that's meant to say is the following. So let's go back to this picture. This is my state space of my world. These are my trajectory parameters. Suppose I have an obstacle that appears here on the right. What I know is that the one super level set of W associated with all possible values of x1 that make this greater than or equal to 1, this object is going to contain the set of trajectory parameters that can actually intersect with x1 starting from that initial condition set. So as I vary these obstacles that exist on the right-hand side, in fact, I'm generating these one super level sets on the left-hand side that actually describe the unsafe trajectory parameters. And in fact, it's an outer approximation to it. So what do we want to do now? If we want to do online optimization, this is the entire story. You now have your obstacles. You want to ensure that this W function across all those obstacles is less than 1. And just infamize over your trajectory parameter space. And that cost function J can describe any possible cost function that you care about. Maybe getting to some location as quickly as possible. Maybe minimizing energy. It doesn't matter. It's just a function of your trajectory parameters. OK. The really amazing thing is, in fact, this is also a semi-definite program. And I should have said, semi-definite programs, for those who don't know, are really amazing because they're convex programs, although they have some troubles with scaling, as I'm sure someone will bring up in a moment. So the thing is, you can optimize an arbitrary cost function, and that cost function can be a function of the entire state space model. It can be that full high-fidelity model of the system. It doesn't matter. And in practice, as I mentioned, you can actually represent the obstacles as semi-definite constraints. And what that means is that this optimization program, at least in its constraints, is going to look convex. If you select your cost function carefully enough, it can also appear convex. And that's really great because it suggests to us that we can run it really, really fast. OK, so my students were very, very excited about this. By the way, any questions so far?
So the optimum function you're calculating, so is that you define it or you calculating your process?
So the question is, am I computing the Lyapunov function through the process, or is it defined a priori? I'm computing it through the process. So my optimization problem, that semi-definite program, is actually computing the V. And I'm doing it using sums of squares programming. OK. So my students were excited about that. Any other questions, by the way? Yes?
So do you assume anything about the set K? Is it convex or something?
At the moment, no. It can just be a semi-algebraic set. So any semi-algebraic set that you care about. By the way, I'm parameterizing my trajectories here. A question that I typically get, it's a really good one, is does that mean I'm fixed to only use like a fixed throttle input and a fixed steering input or something like that? No. In fact, they can be sort of varying. So they could be like a sinusoidal input if I wanted it to be, as long as I could parameterize that input. OK? And we'll show you what that looks like as we keep going. Any other questions? These are great. OK. Cool. So semi-definite program, convex, things must be great. OK, so we said, great, our obstacles are boxes. That should be really easy. OK, and then we started running it, and it took us like 17 seconds to solve. OK, so not fast enough for real time. Did a line, boxes are represented by 4 lines. That should be really fast, right? That still took a second. So where do I go next?
K is convex?
For these numbers, K is not convex. It's well, in this instance, K is convex, sorry. It is, but we're describing it as a semi-algebraic set still. So we're describing it by just using unit interval type constraints. OK. So my students are clever. They said, box doesn't work, line doesn't work, point, right? OK. So if I have an obstacle here, these are the unsafe trajectory parameters. Amazing. Let's discretize the obstacle. OK? Not so smart, right? Because those obstacles certainly do not represent avoiding the obstacle. Right? Because I can generate a trajectory parameter there in this light green. And in fact, as I flow it forward, it can actually intersect with that obstacle, right? So back to the drawing board, right? Or not. So they said, why not just buffer the obstacle? OK? And then if I buffer the obstacle, well, then what I can do is select these points on the buffered obstacle And then hopefully what I can do is generate an outer approximation to the unsafe trajectory parameters. And in fact, that does work. The important thing is how do you select the buffer and how do you select the point spacing? And this is where it took quite a bit of geometry to actually do. And shout out to Shreyas Kaushik and Sean Daskov, because what they did was figure out that if the vehicle is convex, there is actually a prescribed procedure to buffer the obstacles and actually select the point spacing as a function of that buffer size selection. And in fact, that can be pre-computed offline. It's just a function of your vehicle footprint. And the obstacles in this instance just have to be polygonal. Okay? And you can generate an outer approximation that you can use at real time in order to generate the unsafe trajectory parameters. Yes?
Did you just use the convex hull of the object?
So back here, use the convex hull.
Convex hull of the original object, that would reduce the number of points you need.
Um,
Also, it would include every plan.
Yeah, so at the end of the day, even if I used a convex hull of this set of this obstacle, I would still need to figure out what the unsafe trajectory parameters are, right? And in that instance, I'd still need to represent the obstacle as an optimization problem over my trajectory parameter space, and that's still not easy to do. Good question. OK, so if you're interested in the details, by the way, please do take a look at this paper. It's like 50 pages long, but most of it is literally describing this algorithmic procedure to actually discretize an obstacle in a way that you can provably ensure is safe. The last step here is we wanted to actually ensure that we can construct a planner that can use this type of representation in a way where we can make guarantees about safety. And in order to do that, we need to select the time horizon over where we're actually constructing the forward reachable set. In order to do that, we make two additional assumptions. The first is that we have a bounded amount of time to do our planning. It's not really an assumption, it's life, right? And the last thing is, we want to assume that there's a maximum possible stopping time. And what I mean here is that there's a maximum possible stopping distance, and that can translate by doing some arithmetic into a stopping time. And if we use these two assumptions, the way that we want to do planning now is that I'm performing planning in a receding horizon way. So while I'm applying the plan that I've generated previously, I'm using the plan, while I'm applying the plan that I generated previously, I'm generating the new plan that I'll apply when I arrive at that location tau plan away. Okay, so what may happen as I'm operating my vehicle is because I'm solving some optimization problem, after tau plan, I may not actually find a solution. So in order to ensure that we don't run into any problems, we want to make sure that we have enough stopping distance. Okay, and that's going to set a lower bound on what our time horizon over which we can generate this forward reachable set, or how big the forward reachable set has to be in time. Okay, the next piece of the puzzle is, well, what I'm going to do when I arrive here at this location tau plan is apply the plan that I've constructed during this length of time. In order to do that, I now need to ensure that this time horizon contains both a planning time and a stopping time, because now I've computed this T-min that describes the time horizon over which I operate. So this gives us a really strong set of inequality constraints that describe what our sensing horizon needs to be and what our planning horizon needs to be. Great, we have all the pieces. And now we can start generating cool animated GIFs, right? OK, so this is fun. This is it working in simulation. OK, we'll get up to real examples, I promise you. What we wanted to try to do is I wanted to be convinced that this wasn't conservative. The reason is we're making a pretty strong assumption here, which is we're simplifying our model, representing this really complicated vehicle model using a really simplistic one and introducing that gigantic G function that could introduce a lot of uncertainty. So in order to do that, we wanted to do a comparison. And the two comparisons we could think of were RRTs, because that's what a whole community does, and another one, which is nonlinear model predictive control. And in fact, in this instance, there's beautiful libraries available out there. We didn't want to write our own. So we used one called GPOPs that uses pseudospectral collocation in order to generate an optimization problem that it can solve in order to do this type of optimization. In any case, each of these methods also discretizes time in a sense. And because they discretize time, they also need to have a buffer around their obstacle in order to really say something about safety. So what we wanted to do was figure out what the right size buffer would be for these types of planners so that they can get the best performance that they can. So what we did was run all of these planners in arbitrary worlds and where we varied the buffer size without any real-time constraint. And what we verified are the number of goals that they reached, because we had like a final location that they had to arrive at. And what we wanted to evaluate were the number of crashes they had while doing it. Okay, and the results are not too surprising. As I increase my buffer size, the world starts becoming like a maze, and I can't get out of the maze. So I can't get to the goal, but the benefit here is that I don't crash while doing it. Right? So it makes sense that the number of goals decreases as the buffer size increases, but the number of crashes also decreases, right? Now, in fact, what I'll argue for just a moment is that basically this is what a lot of self-driving car companies are really doing at the moment, which is that they're buffering the worlds to be really, really large, or obstacles to be really, really large, to ensure that they don't actually run into anything. And the penalty that they pay is a non-trivial one. They drive really, really slowly. And again, you may be comfortable with that. I would rather drive down Plymouth at like 100 miles per hour if possible, right? OK. So what we did was do an evaluation. And we took the best buffer size we could that we generated from the previous one. What was it, Trace? Do you remember? 0.45? Yeah. OK. And we gave that to RRT and nonlinear model predictive control. And then we set our tau plan to half a second. We had a sensing horizon of 4 meters. And then we ran our planners in the real world, or in a simulated world across a bunch of different obstacle courses. And what we saw is that our planner wasn't that conservative. We could still ensure that we didn't crash, which is great. RRT, gets to the goal a lot less, but has a lot more crashes. And nonlinear model predictive control really struggles to get off the start line, because it's really hard for these nonlinear programs to actually be solved. Now, again, there are better solvers potentially out there. We just went with one that was commercial because it was the easiest thing that we could do a comparison with respect to. So that's all great. Let's start showing some videos. So I said, great, let's try to get this to work in my lab. And hopefully this will start playing. Each clip is a single take because I want to convince you that the worlds are really random, okay, that I'm not fooling with you. And I forced my students to tape this like an Inarritu movie, so it's like Birdman. Everything is one shot, okay? And nothing is known. Everything is planned on board. And you'll see this thing running back and forth. And I think they'll walk you through what this is. But let me skip ahead a little bit. Okay, and what you're going to see is that they're just going to start throwing obstacles. And you'll notice this is like a 5-minute movie. It's available on the website, by the way. But what we wanted to show is that, again, we could just keep running this thing over and over and over and just keep throwing obstacles. And again, we wanted to show that the robot is actually operating at real time, 1x. In fact, the world's generation is what's taking 16x. It's kind of the opposite of the way that most robotics videos work at the moment. Okay, and I'll sort of skip ahead here, but you'll see that they'll start getting really mean, start throwing lots and lots more obstacles. And again, everything is random. And if you're really interested in this video, please do take a look at our website. Okay, and at the end, they start getting less random because they wanted to show, hey, does this actually work in a structured way? They start getting even more sort of bold. They put themselves in the video. They seem to believe that they're bulletproof. Okay. And again, it's planning everything on board the vehicle. You can see that they don't really believe in their planner. Okay. You'll see that they think this one's fun. So you'll see that fun in this instance actually starts moving around soon. Okay. Anyway, yeah. And I think this one's a good one, right? There. Okay. Okay. And then, they get more and more bold. It's like one of those safety trust tests. Okay. Okay. Great. All right. So then, we have some collaborators at Ford who said, let's actually try to get this working on like something that looks more like a vehicle. Again, a Inarritu movie. Obsessed, apparently. They started getting this to work on an actual sort of platform that looks like this. And again, you can find the video online. They start throwing obstacles around, whatnot. Then I said, great, let's actually throw this on a CarSim fusion model that actually is representative of the AV platform that we, as a group, have access to. And so what we wanted to do is run this model with this Ford Fusion model out at MCity, but in a virtual version of MCity, because we're still working on trying to translate this onto a hardware platform, which is, I think, our summer project. And you'll see, I think the speed limit out at MCity on this outer loop is about 60 kilometers per hour, and we're placing obstacles basically at the limit of trying to get up to that speed. And it'll do fun stuff. And again, it's doing all the obstacle avoidance in a provably safe way, discretizing everything in a way where we can actually ensure that things will work out nicely, et cetera. And I think, again,
How did you verify that your G function was correct when you changed platforms here?
Yeah, so
that had to be hard. So
fantastic question.
Then
yeah.
simulator might have 200 states, right, in that model?
Yeah, so in practice, it's a really great question. What I know, and I mean, what we need to do as we move forward is, build a better way to build that G function. What we do at the moment is basically sampling, and we try to sample our system over an arbitrary, really large number of states, let that run on a GPU over a really long period of time, and then try to bound the difference between what our low fidelity model says and our high fidelity model says. That's hard to do, I agree with you. We're working on techniques to make that more accessible by literally taking in the high fidelity model, bounding parameters inside of it directly, like the friction cone, and introducing that in a way where we can construct that G function directly. There are also sums of squares based techniques to try to do this, but I'll spare you the sums of squares nonsense for a moment.
Just building up on that question, if you're assuming that you already have access to, in this case, a 6-dimensional model, you're truncating that to a 3-dimensional model. What if the 6-dimensional model itself is not represented in the vehicle?
Totally. So, yeah, so let me repeat the question. If the 6-dimensional model isn't actually representing the true behavior of the system, how do you actually ensure that you can bound safety? That's a really great question. Again, at the end of the day, the ways that car companies are thinking about verifying the models that they construct is running them. So at the end of the day, they go out. I mean, part of the experience that I had at Sault Ste. Marie was that they put the car inside of a fridge, and they ran the car inside of a fridge, a really, really low temperature fridge, and actually ran the vehicle forward and actually tested different types of parameters inside of the system in order to actually construct a reasonable representation of the system. I'm not saying that that disappears from the story. What I'm saying is that when we take that model and the uncertainty we have with it, we can actually incorporate that in a meaningful way while doing our planning. So we can also do this with quad rotors. In this instance, this is a 13-dimensional representation of the system. In fact, in this instance, we are not creating a low-dimensional model that's like 3 or 4 states. We're actually using the full 13-dimensional model of the system. This is cool. And in this instance, we're using a slightly different way to compute the forward reachable set, but it's more or less similar. We can do this with walking robots. We're getting closer and closer to trying to translate this onto CASI, which is in my lab. And in this instance, what we have is a representation of what the safe region is for this system. And we're actually selecting trajectory parameters in this instance, which correspond to sort of the gate library that Jesse's group has been developing, and optimizing over that safe gate library space in order to ensure that we can follow paths in a way that ensures that the robot doesn't fall over. In fact, we've also done this formulation with looking at this more like a reference governor. And in this instance, we're computing something that looks like the viability kernel for these walking robots. And again, in this instance, instead of always selecting from a safe set of trajectory parameters, we're instead correcting them, like I described in my related work section. Sort of skip ahead here. And again, our goal is to now start translating these planar models. And again, it's been really hard to get sums of squares and these types of optimization techniques to work for big systems. We're slowly making progress in translating these onto the types of systems that people care about, which is basically the work that we've been pursuing in great deal in my lab. We keep moving here. Just in 5 minutes, I'm going to talk about how we do dynamic obstacles, just because I think people will be interested in that. OK, so now we're back to our same world. Now we have moving obstacles. We certainly need to be able to say something about prediction here. And we're going to assume something fairly strong, which is that our predictions are conservative. They don't need to be accurate. They just need to be conservative. Okay? And in this instance, even if we had that prediction, we may be a parked car, and someone may run into us. It's not our fault in that instance, but certainly that can happen when things are moving in the world now. And so we need to stop talking about safety in this instance and start speaking about a different notion, which I'll call not at fault. And in this paper, we developed this notion of not at fault behavior. And in particular, we focused on this definition, although it can be generalized to other notions of not at fault. So in this case, we're saying an autonomous vehicle is not at fault at time t if it is either stationary or not intersecting any obstacles. OK, so using this notion of not at fault, what we're going to try to do is generate trajectory parameters that are safe. And the way that we'll do that is instead of using this W function, we're going to now use that V function. And the V function satisfies a very similar type of inequality constraint when it comes to speak about the forward reachable set of the system. And what we can do is discretize this prediction in the same way that we discretized earlier in order to generate a representation of obstacles to ensure safety. And in fact, in this paper, we show how to discretize in time as well in order to ensure not at fault behavior. And that's described, again, in this archive paper that you can take a look at. And the funny thing here is that we basically took this planner and said, hey, left turns seem to be a really hard problem that people in the self-driving car space care a lot about. Can we not now start doing left turns in a not at fault way? And so you'll see, again, we're taking these predictions, it's thinking cautiously and executing things. And again, I like to be really mean with my robots. Probably the first one who dies in the apocalypse. You'll see now we have predictions of everything surrounding the vehicle, and you'll start seeing pedestrians coming out. And again, we do evaluations. We really believe in that in my group. Obviously, everyone does. And in this instance, instead of using a RRT, we use sort of a generalization of it that's called the state lattice. And what we see is that for a variety of different sort of platforms, we have no at-fault collisions. We actually can get to the goals pretty frequently. And we can actually get really high average peak speeds and average speeds, which is great. So then we started doing demos up in ggBrown. And we sat up at the top and recorded our Segway platform running around in the atrium and actually showing that we could generate behavior in a nice way for this type of system with virtual obstacles initially. And again, I think this video is online as well. You'll see that it can figure out how to get around these things.
You're spoofing the robot into seeing the obstacles.
That's right. We're spoofing the robot into seeing the obstacles. And the reason we did this overhead is so that we could see it from top down. Again, you can find this on my website. We start doing really mean things like doing Mario-related bad guys. Yeah.
So why is this the right definition of a not fault? For example, like if I step in front of a moving train and like I stop, then technically I'm not at fault.
Totally. That's a really good point. So in fact, this definition of not at fault, like if you created one where you incorporated the reaction time of each individual, so you said, hey, each element out there in the real world has a braking distance that looks this large when they follow the speed limit, and they have a reaction time that corresponds to this length of time. In fact, we can generalize everything I present here to that notion of not at fault behavior. So like basically nothing really breaks here in terms of the theory. It's just you have to tell us what the appropriate definition of not at fault is. This is one to get us started, but as we move forward, we're thinking about other ones that may be more meaningful, but none of the theory changes in any grandiose way. Then we wanted to show it worked on a vehicle. So we started, again, doing sort of spoofing demos, where now, again, all we're going to plot here is the spoofed obstacle, not the human. And you'll start seeing that it can do lane, like overtake maneuvers and whatnot. And that's really cool. And again, these videos can be found on our website. It starts, again, doing really cool things. Because I'm a believer in generalizing whenever possible, we started doing this on and we have a sense of humor. Okay, it's the end of the semester. Okay, maybe we'll put this video up. Okay, the thing I should mention here in the interest of time is that we have a lot of related extensions to this type of flavor of thinking. So in fact, this type of lifting strategy can allow us to formulate optimal control problems in a convex way. And in fact, we've shown how to do that for hybrid systems in a way where you don't have to be dependent upon your initialization. For hybrid systems, this is particularly problematic because you typically have a combinatorial optimization problem where you have to think about the type of sequence of contacts that you want to undertake. This method, this relaxation method, can allow you to overcome that problem. And as one of my students, Josh, presented this morning in his thesis defense, there's beautiful ways to also extend this to be able to do things like globally optimal SLAM. And in this instance, you can really increase the size of the problems that we can solve because of the structure that you have. So earlier on, we're sort of in the 8 to 10 dimensional state space world. In this instance, we're solving SLAM problems globally optimally with hundreds of constraints, and we're talking about under a minute or so. So you can really push that higher and higher and higher, and it becomes really exciting. I'm going to skip quickly to the end here and mention sort of everyone who at least was in the presentation today. And again, these are the folks at Michigan who are really doing the heavy lifting, I'd say. And then I will end with this last video and questions. It is actually. And I'll point out, again, we're not making any limitations on the dynamics of the Millennium Falcon in this instance. We're not using a near hover model. In fact, it's the full nonlinear model of the thing. That's how you can get a barrel roll out of these systems. So we're really doing it in our lab. OK, any questions? Please, yes.